In terms of material, 2D materials are the in thing, is the buzzword. These are essentially monolayers, single layer crystalline materials.
They're only like nanometers thick, right?
Yes, so they're atomic scale, and then you layer them up, and graphene, for that example, it's more recent and it's happening. But unless you have a compatible device interface, all critical advancements will not happen.
Welcome to It's a Material World, the show that uncovers why material science will change the world, with your hosts,
Praneeth Upadhyay
and Tom Miller. In today's episode, the interface between MSE and electronics.
So, our guest today is Dr. Himani Sharma, a material science and engineering professor at Georgia Tech. Dr. Sharma has a great deal of experience in developing technologies in the consumer and medical electronics industry, and she has authored 60 publications, co-authored 1 book, 3 book chapters, and even 1 pending patent. Wow, you've really done a lot, Dr. Sharma. Welcome. So for our listeners, can you tell us a little bit more about your current role, as well as how your passion for material science and electronics got you to where you are today?
Hello, everybody. Like Praneeth said, I've been at Georgia Tech for a little longer than 14 years. I'm currently a lecturer in School of Material Science and Engineering, and I have had this privilege of teaching undergraduate students only in past few semesters. So this is technically my 3rd semester teaching undergraduate students. Before that, my focus has been purely in developing materials for electronics. We have done mostly processes that will develop passive electronic components. There are active components and passive components, and we can get into details of that a little later. But essentially, 85% of the real estate on your consumer electronic product is a passive component. So capacitors, inductors, resistors. So my work was focused on making them better, making them smaller, and making them fancier in the way they function. So that's what I've been doing. See, 25 years ago, when I was still an undergrad, thinking of pursuing my higher education, we didn't have material science back in the country that I grew up in. We were mostly talking about, pure sciences and applied some of pure physics and chemistry and engineering concepts. Material science wasn't as popular or known field. So when I started doing post-PhD, my doctorate, I was doing work on developing CNT-based transistors. I came from chemistry background, didn't really know much about transistors of all things. And CNT, that field was so new, this was about 15 years ago, that MOSFETs with CNT-based were gaining interest. And I didn't come from that background. So I get to learn a lot while I was on those job fronts. So I learned and realized that everything that pure physics and pure chemistry was leading to was into materials. And somehow I got into doing electronics, an electronic material. But if you look around and you saw transportation, you see agriculture, you see telecommunication, all the electronics that go into any of those areas are driven by materials. So gradually, slowly, but very steadily, that interest kind of developed in me. I was fortunate enough to work with a lot of industry, semiconductor leading industries in the US. And one of them, very prominent one, was bio implants and bioproducts, that what they would make. And I was put on a project that said, well, you're going to develop a component for a pacemaker. And I could see a real world application of something that will be done in the lab and actually make somebody's life for better. That kind of drove the intention to continue and pursue MSE and the research in electronics.
You kind of touched on this point already, but just to elaborate a little bit further, what exactly is the role of material science and engineering, in particular, in the electronics field today?
So material science and engineering, right? The term you said, I want to first explain it in 2 ways. Yeah, there are 2 terms in one MSE. There's material science and there's materials engineering. And material science is essentially, you look at the structure of a material and you see how its properties are. And material engineering is where you take these structure and these materials and you correlate it to design something for as a product, a consumer product that can be used for a number of things. So MSE plays a major role. It is the heart and soul of any electronic that you can think of. It's not just one aspect, not electronics in one particular area, but if you talk about health, you talk about national security, you talk about transportation, you talk about structural engineering, plastics, everywhere. You can't think of building a product, an electronic product, without materials in them. The question is, what drives it? What are the factors that influence these engineered materials? Why, what role that they play? And I've got a list of those. The first one is the economics and the cost, developmental trends, depletion of the traditional materials, just because overuse. Market drives, consumers drives the need. Of course, you have environmental requirements these days as well. And because all of these are continuously changing and evolving, we need to keep up with materials and the processes that they're made up with. So MSE, to say the least, is the core of all the electronics that you use and their performances that are being carried out.
That's awesome. That's basically the purpose of our podcast here, is to show how material science and materials engineering can make that impact in various industries. So I'm glad you really emphasized that. So let's elaborate more on manufacturing electronics. I was wondering what sorts of materials are used in manufacturing electronics, and why are these the materials that are selected?
So if you just look at broadly, anything that you can see, metals, polymers, ceramics, composites, anything that are prominently available is used for electronics. That's no question. But let me just say that we'll classify them based on their application. There are materials that are driven by just the device. When I say device, I mean the transistor. The transistor in the integrated chip, the IC, okay? We'll call that as a device. So there's materials that are device-driven. There are materials that are interconnection-driven. You have a device, but it needs to talk to other of the components in the area, in the entire system. So interconnection plays a big role. So there are materials that are driven by this interconnection. And then there are materials that drive system performance and their reliability. You just don't want material to work. You want it to work repeatedly for over years. And with repeated uses, we want to make sure that it's reliable and it can stay and take care of itself. So broadly, I'll classify them with these three classes. So let's talk about the device materials first. Device materials, what does it form? Semiconductors, which is the most common one that you use. Silicon. And we are now graduating to other ones, 3-5 semiconductors, right? There's gallium nitride, GaN, like they say, or gallium arsenide. And all of them, they form the basis of your device. When I call device, I mean, again, the transistor and the basic transistor onto a chip, an integrated chip. So those material. Then the interconnection that we were talking about earlier. In today's world, remember, with such miniaturization happening, right? Your phone 10 years ago is now on your wrists, right? It's that tiny. It has all the features that one did and more. What did it take? It took a lot of development in materials and processes to bring all of that in a small thing. But one thing is that all these different small materials and devices that you have, they are talking to each other. They are making interconnections. Those interconnections are the ones that will drive future technology in electronics. Because the device material, they don't really have a blockage as much. You can always have ideal gallium arsenide and their combination of other materials and other 3-5 electronics, semiconductors that can do much superior properties. But when you put them into a real device, and they don't really communicate well with each other because the interconnection is poor. The amount of power that you are putting through them and the amount of signal transmission that's happening through it, it's much more for those interconnection to handle. So materials that are being used essentially are copper. What is what's usually used? Very thin amount of gold. That's what is used for interconnection. But remember, they're all getting 3D, 3-dimensional. Because you have devices sitting on top of the device and they need to talk. If you spread them out and put them laterally, those two devices, the performance of your final electronic product won't be great. And those come for different reasons that we can probably focus on later on. So you want one device to sit on the top of the other, and the communication between those will have to have with very fine copper, very fine gold that's being used. So those are interconnection driven material. CNTs also are being used. They haven't really picked up that much. The other one that we were talking about was the system level reliability. Not just you want the interconnection, but you want it to be reliable. You want to protect a solder, a simple solder that you have. You want to protect it. You want to fill them up with other polymers to give them a cushion. Think of this as a pillar that's standing, and if you have polymer backings or settings that will hold the pillar together, the amount of wear and tear will be much less. So underfills that are polymer composites or epoxy filled with silver, those kind of materials are other ones that plays a very important role. But so broadly, I could classify electronics materials into these kinds, but more fundamentally, they're electronic materials and they're photonic materials. Because what does an electronic do, essentially? It does a two purpose. It generates all these signals and it transmits all these different signals. And the way it does that is through all these different materials and the small devices that are very beautifully designed such that they're just the right properties to minimize the noise, to elaborate the signal that we are trying to look for.
So to elaborate on some of those limitations, what are some of the current limitations in the materials that we use in electronics? In particular, the materials issues with respect to connectivity issues that you had kind of alluded to in that last response there.
The major limitations with miniaturized electronics that we have these days is essentially the interfaces. It is not the material per se. It is not the device per se, but the interface between the other component that it's making, that becomes the limitation. It's a solder, right? Even if you're talking about simple solder and putting in so much voltage, there's so much current passing through it. What do you expect? You expect there's going to be some atomic diffusion happening. Metals will be diffusing from one end to the other. What would that happen? It will deplete the amount of conductivity that you're looking at. It will generate a lot more thermal problems into it. So limitations currently that I see is mostly for the interface. The other thing is the processing of these material into thin films. We're talking about copper, standard material, standard interconnection, highly conductive in nature, doesn't corrode as much, and it is cost effective. It will do what it needs to do. Problem is now when your IC is gone down to a few millimeters, your interconnection is going to go down to micron sized. When you have a micron-sized copper, you want it to stand only a few micron away from another line of copper. How do you actually process it so that it doesn't have processing issues? I don't want one line of copper to be broader than the other line of copper. They need to be at the same height, at the same thickness, same pitch, because it's going to create all other electrical concerns. There is something called as capacitance or capacitive coupling that will start happening between these copper lines. When we don't want that to happen, it will do a lot of crosstalk, which will again further deplete the properties. So processing and interface, two major limitations in electronics these days is what I would say.
So let's take that back to a higher level. Is interface and processing, is that the reason that if you leave your phone in a car on a hot day, it overheats and you can't use it until it cools down? Or like if you drop your phone in the water, it shorts the circuit. Is processing and interface the causes behind that, or is it something else?
Just the manual or mechanical use of material. The first thing to fail are the interconnections, the interfaces. It's still those when you drop your phone, other than the screen that you see, the electronics inside, the first thing will break will be the solder. It's not as protected. It's the interface again. You are trying to marry two different materials. You want to have them a strong metallurgical bond, and you want to run and rerun with certain voltage, temperatures, and so much changes. Just the amount of shear where the material is going to go through, they are the most prone to failures. And if you're asking me the inconveniences, you see how our electronics these days, they work fantastic when you buy them for the first 2 years. Third year onwards, they have an upgrade and yours starts heating up. I won't call it as an inconvenience, but I wish that material scientists work towards bringing the shelf life of these materials and these electronics longer. Because it's not just, oh, my computer is heating up and I need to change the fan, or I'll go and buy a new electronic. It's not just the inconvenience of the use, but also long-term disadvantages that we're going to all end up with. It's going to end up in the landfill. We don't know how to, so much electronic wastes that we're generating. So inconveniences are more than just consumer related. And a lot of this has to come with much stronger interconnections. When I say interconnection, I mean the interfaces between materials.
Do you think that it's money related in terms of why why our phones, are only great for 2 years? Because then, Apple would want us to upgrade to the next phone and pay money there. Or do you think it actually is materials related?
It's actually a combination of both. Obviously, consumerism is what is driving it. But of course, they are limited by the material, the way they are being processed. Everybody wants to stream a very big video while attending a class, online virtual class, and also talk to their family and friends on the phone, all three things at the same time. We need the power of my computer, processing power, to be over the roof. So with that demand, so consumers are driving it, and companies would take it and say, well, in next 2 years, I'll come and bring you with something. Of course, the infrastructure that I have will only support that level of advancement. So it is a combination of both.
So to further dig into this cost side of electronics and how that plays into the material science, so what are some of the modern cost pressures on electronics? So for example, you had mentioned that gold is one of the materials used for interconnectivity of these electronics, but gold, as we all know, is not a particularly cheap material to come by. So is there research being done into creating cheaper alternatives to some of the more costly materials that have to be used today in building electronics?
Because you're talking particularly about gold, let me talk about it. So we'll start with why gold? Why is gold used in the first place? Because we know it is extremely high in conductivity. Electrical conductivity is high. It won't corrode easily. Its surface finishes are excellent. And it is fairly easy to come by, right? It may be expensive. It's humans who have given it a certain level of importance to the metal itself, right? But among property-wise, you can't beat its electrical properties, their thermal conductivity, and the corrosion resistance. Because of these properties, that's why it's being used. And honestly, it only is taking maybe a very minuscule amount of gold that goes in it. Where does it go? It is used in surface finish of a PCB board. It is also used in wire bonding material because it will solder very well. It diffuses very easily into metals and forms a good metallurgical bond. So it's, if you desire a cost reduction design and you don't mind a slight deterioration in the performance of a material, sure, there are other alternatives for gold. For example, there is something called ENIG, which is electroless nickel gold. And what it does is it is an electrochemical process where you make a very thin amount of gold, and then it's in combination with nickel in it. That makes a good bond of interconnection between the two, sites for soldering. Nickel actually gives you the wear resistance, and gold gives its electrical conductivity. And then the diffusion barrier between the two areas was given by nickel. So ENIG is very commonly used. It uses a small amount of gold. If you want to replace it, the other alternative these days are organic soldering. And they are called as OSPs, which is organic solderability preservative. And they form a very thin organic coating on the base of the metals. Usually it's copper. The material does not give very long shelf life, but it's definitely cheaper than gold. Okay, so that's one alternative. The other one is also called as HASL, which is short form for hot air solder leveling. And what it creates is a layer of tin lead, tin silver, or copper. And it isn't as expensive as gold, but it can result in thicker solder intermetallic, which decreases the solder life. So there are alternatives to gold that are available already. But it comes with a slightly, which is very minuscule, honestly, performance deterioration. And many of the consumers won't even see this. In total honesty, material cost is very, very minimum. If you start with the wafer, if you have to guess, how many steps do you think the wafer will go through from being a wafer and to get to a chip that will sit on your laptop? How many steps? Take a guess.
5?
10.
There are about 500 steps.
Oh.
We were not close.
Okay.
I was closer though.
Closer, yes.
So what you're saying though is that materials cost compared to processing costs in this industry is just totally in a different range.
That's right.
Yeah.
You're using 10 nanometer of gold in ENIG of solder and the entire wafer. It's going to be too little for the other 500 steps that it's going to go through.
Fair enough.
we were so far off. Let's talk about costs a little bit more in the realm of Moore's Law. So for listeners who may not know, Moore's Law refers to the perception that, the number of transistors on a microchip doubles every 2 years. I wanted to ask you, how have materials innovations contributed to sustaining Moore's Law, and do you think that is sustainable moving forward?
Moore's Law is my favorite. Because, you know why? Because first, like you say, it's a perception. It's a prediction. And why is it my favorite? It's because it shows the immense amount of advancement that humans have done in terms of technology. And let's take one step back again and understand this law. And Moore's Law is what it's saying is Moore's in 70s, an Intel fellow, he said, I'm going to put that number of transistors on my chip, okay? And the more the number of transistors are on the chip, the more my performance or my computing performance are going to be. So the more number of transistors means faster computers, faster processing speed, and much more things that I can do with it. So everybody started getting greedy. I want to put more and more and more. So let's say I have this piece of wood in front of me. I don't know why, but this was lying here. Somebody might have dropped it. But that's the real estate you had in 70s, let's say, okay? And you had 2,500 transistors sitting in it. In the same space, in 2020, how many do you think transistors have been put on?
Oh gosh, another guessing game. I'm scared. I
don't think we're very good at this guessing.
Well, so I know transistors now are down at the nanoscale. So very, very small.
That's right.
So this is me taking a approximation at how large the area you're providing us, but be on the order of billions at this point, right?
That's true. And this time you're bang on, you're correct.
Yes.
Right?
Good job, Tom.
Right? So because we have those sheer number of, I want you to just think what it takes to bring those many number of transistors onto a small space. What is the transistor? Transistor has only three things. It has two electrodes. One is called a source, the other called as a drain. And then there is a little switch that will turn it on and off. It's called a gate on top. Those only three things. And those three things are getting smaller and smaller in size. And the way we are right now, there are orders of few atomic spaces apart from each other. It's mind-blowing to just see how this is done. And so that is why I feel like Moore's Law is fantastic. Every 2 years, they say it's dead. They've been saying this for past 10 years. Moore's Law is dead, Moore's Law is dead, Moore's Law is dead. But they have been pushing it a little bit. Moore's Law has definitely slowed down. But every now and then, the advancements keep coming in. And one of my favorite examples of telling how this is now introduced is photolithography. So how does it all start? You start with a wafer, okay, and it has these billion transistors on them. How do you make these billion transistors? By a process called lithography. It's called photolithography, where essentially it's like when you have a negative of a picture long time ago when you had it and you developed it. It's a very similar process. You have a mask and you have a pattern, geometrical pattern that you want it on your wafer. It's put through the light source, and the light source actually makes an impression and leaves the geometric print on those. When you're working with nano dimensions, and in some cases even angstrom distances away, you have to work with very short wavelengths because you want to make these features that fine. You don't have a knife that would go and drill out a 10 nanometer dimension. That's you need light with very short wavelength. And what we see visibly is usually between 400 to 800 nanometers range. But with processing these, the light source wavelength is down to 193 nanometers. It's like deep ultraviolet radiations. Now, so what does that take? These light sources are basically lasers. And lasers, what are lasers made of? Lasers, they have, gases like carbon dioxide, and then you put a lot of current in them, you ignite them, and then it will generate a laser that can be fine-tuned to the wavelength that you're looking for. So they came down from 365 to 193. And then they said, well, we're going to make 150 nanometers of wavelength light source that can be fine-tuned to that one. And they put multi-million dollars, tens of millions of dollars into it. And that boom, that didn't work. So they're like, what do we do now? We need to get to smaller dimensions and 10 nanometers, 14, 15 nanometers that you're talking about these days. So one of my favorite tricks that I hear, what they did was, these laser lights goes through different lenses, hundreds and millions of them. They're very finely balanced out. They realized that in order to make it shorter wavelength under a lens, if they put a little puddle of water, the light is going to pass through that water and it will shorten the wavelength. There you go. You have a shortened wavelength underneath. But think about it. These massive machines with very fine and very advanced electronics in it. You put a puddle of water under a lens, a small lens. It takes a engineering marvel to be able to do so and actually make that happen. But they did it. And that's why 10 nanometers and 13.5 nanometers is possible. So Moore's law is being driven. Of course, it's slowed down heavily and probably further. It's going to, die at some point. But it just brings up the advancement in technology to another level. Photolithography process, the materials, the lasers, the mask, the alignments, you name it. All of that comes from MSE.
So moving out of the space of, how material science is driving innovation on the processing side of it, let's also talk about, the end of the life cycle of a lot of these electronics. So, what roles does advancing material science and engineering play in reducing the harmful impacts of electronics waste, also known as e-waste for short?
So manufacturers, a few years ago, what they did was they realized that these electronic waste is a big nuisance. What do we do? They said, well, we'll give you an electronic that you can take some parts off and replace the parts of your product will be as
right.
good as new. So those replacement parts were out there, and we'll take those parts and recycle it the way they wanted it to do. Those things kind of didn't work much because they could not really keep up with the recycling process. And the manufacturing folks, they decided there is a need to design the new materials in general. We have to start with a material that is biodegradable. So there are a couple of things that I saw. There is a group in Stanford University, and they developed a fully biodegradable electronic circuit. And they made it with natural dyes that can dissolve in acid, and the pH is going to be very, very high. Dissolve in acid, but if it is a purely biodegradable circuit, that's the future. That's what we are looking at. That's one of the options. The other areas where some people were doing is they were pulverizing this e-waste into nanodust by cooling the various materials and then grinding them up into homogeneous material that are easy to reuse. There's a company, and it's based out of Canada, and they said, well, I'm going to use a technology that will use minimal amount of water and energy, and it will separate the metals and the non-metals from your electrons. And I'll use this with sonic vibration, and we'll use this recycled water and then separate this out. So there are ideas and some of the research that's being developed on it. So material science can help. One of the more recent ones, and I think it's not as electronic waste, but what people will appreciate is, about those packing peanuts?
Yeah.
Right? And they were all styrofoam based and polymer based for the longest time. Do you know, are they still like that?
I think those have moved to, so correct me if I'm wrong. It seems like you definitely know the answer to this, but the things that I've seen is, one, I've seen some packing peanuts now that are completely corn-based, which is interesting. And then
I've seen cellulose-based, yeah.
Right, so cellulose-based ones.
It will dissolve in water. You let it, if you have a large bag, you let it stay there for a longer time period, but it'll do the job. We want similar kinds of research that goes into making electronics. The problems are the heavy metals. We're talking about gallium here and arsenides and indium and whatnot. So those heavy metals are the problem. So all the ones that I talked about, whether it is, separating metals from non-metals, sonic vibrations, or even magnetic fields to separate that out, those are what I feel are the future of controlling e-waste. Of course, all of this comes with consumers being a little more conscious about it and they doing their part.
Cool. So let's talk about that more. So in terms of the future, what would you say is the primary advancement in MSE that you see on the horizon that would drastically improve the electronics industry?
Material per se, there's not as much need of forming new materials or coming up with new material altogether. When we started this conversation, we were talking about the problems that we were having with the interface. It's about the connection between the two. You have a metal in one place, you have a ceramic in the other side. Your metal is sitting on top of a ceramic. You need them to talk and do what they need to do. Those are the problems. And I think the advancement will only come when we're able to focus and come up with solutions of those interfaces. So coming up alternatives for gallium arsenide, gallium nitride, or silicon, I don't see them driving any groundbreaking research. But yes, if you come up with processes that will help you make more reliable interconnections, it will help you make something that can withstand temperatures and voltages and other things. At the interface level, at the communication level, reliability level, those will be the advancements in what I believe. In terms of material, 2D materials are the in thing, is the buzzword. These are essentially monolayers, single layer crystalline materials.
They're only like nanometers thick, right?
Yes, so they're atomic scale. And then you layer them up, and graphene, for that example, it's more recent and it's happening. CNT was that.
Quick question, what is CNT?
Carbon nanotubes. Yeah, those are the ones that they were promising and they still are. But unless you have a compatible device interface, all critical advancements will not happen.
But which is also to say that though it may not be developing a new material per se, like you said, there's certainly a flavor of MSE that comes about with studying those interfaces between materials and really optimizing the type process control required to really get that to the place where you deem it necessary to make those leaps and bounds that we need.
That's correct. It's definitely material science, right? Surface phenomena that's happened. And it's just that we have to look deeper into these interfaces, try to come up with more engineering designs that can bypass or impede some of the challenges that we are facing these days.
That's incredible. It sounds like there's been a ton of really awesome electron microscopy done on some of these materials. So I should go Google around for those.
Yes, the characterization is big. Material science and electronics, they purposefully fail the electronics at different conditions. And then all they want to do is make cross-sections after cross-sections so they can throw it into SCM and TMs and all this beautiful in situ characterization that's happening these days. Put the current while the sample is in transmission electron microscope. It amazes me how much progress we have made in the last 25 years with all these beautiful technologies out there. And thanks to, material engineers all over the world. Of course, it's more interdisciplinary. It's not just physicists and engineers from other backgrounds that all come into play. But material science is what it drives me nuts even now.
So how has graphene played a role in electronics packaging? And do you see it being used more often once it can be manufactured at an industrial scale? So
yes, graphene is one of the new materials. And you know how it's being publicized? If you read it out, it'll say graphene is the thinnest, it is the strongest, it's the most flexible material that's known. That's how people who sell graphene really sell it at that. And that is true. It's really true. Just to give you some numbers, it's 200 times more stronger than steel. It is 97% transparent. It's extremely light in weight, and it's flexible and stretchable. And all of this is true. But in terms for electronics, it's thermal conductivity and it's electrical conductivity. Both of those are why it is such a fascinating material to work with. They say that graphene has got very high electrical conductivity because it is in overlap semi-metal. That's what it's a lingo, a technical term for why it has this super high conductivity to it. But again, if it's a monolayer, if it's a 2D graphene, you get all the ideal properties into it. But manufacturers are dealing with challenges where they get these multiple layers. They've got so many layers and they're all entangled. They're not really we need this one layer stacked neatly over the other for it to give the final properties. And that's not happening. That's where manufacturers are getting into two-dimensional processes. They say that, there are certain nano CVD-like processes, where 90% of graphene can be a single layer. And they say if we are able to manufacture in large quantities, it will be 1 million times faster than graphene, which is deposited by CVD. It is also 100 times faster in terms of conductivity, the graphite, which is used in batteries. So again, because it has such beautiful thermal conductivity, it can be used. One additional thing why it is picking up that much interest is because it has good compatibility with silicon. The CTE, or coefficient of thermal expansion, of graphene and copper are very similar. And so for packaging application, where you need zero stress between an interconnection. So if you have graphene-like material, that can act as another substrate on the other end. The CTE mismatch is less, and it's called as a zero stress packaging. And that can be used as a heat spreaders and packaging. So it has a lot of application. Also, flexible and wearable electronics. They can take big advantage of graphene because, again, it has beautiful mechanical properties and it has high electrical conductivity. Right now, these touch screens, what is the material that's made of? So ITOs, okay? This is indium tin oxide. So ITO does its job beautifully. The only problem is it's very brittle. So if you have graphene-based electronics, which are flexible, and they have these 97% clear. So it won't have that turbidity. It can be used. So all these shatter-proof glass and all, it's still glass, not graphene yet, but graphene has potential application in those areas too. So it's combining its thermal properties, electrical properties, optical properties. So graphene is the new CNT, carbon nanotubes, that we're talking about.
That's
Again,
awesome.
I think the limitation would be it needs to talk to other thing, and the interface should be fairly compatible.
And so one quick term there, you said it's a zero overlap semi-metal. So Could you just define that term a little bit and unpack exactly what that means?
So semi-metals are basically materials that have properties in between metals, non-metals, and semiconductors. So we know there are three classes of materials, right? There is metals, there are insulators or dielectrics, and then there are semiconductors. And then there are a few materials that are semi-metal in nature because their properties are between the semiconductor and metal because they're very beautiful electronic configuration. They have this partially filled orbital that the electrons can jump and hop around in a way that it can very easily be tuned into either semiconductor or fuel. And graphene has those properties because of its very tight structure. The carbon-carbon bond between graphene is much tighter than any other carbon product out there. And because it is such strongly held together, very covalent bonds, even thermal vibrations won't jiggle or won't perturb the bond between those carbon atoms within graphene. And therefore, it has very beautiful thermal properties. It's used as thermal interface materials, or TIM as they call them, because of this semi-metal behavior.
And so is that zero overlap parts that come from its electronic configuration? Or
Yes,
is that,
it is from the electronic configuration. The 3p and the 3d orbitals, they kind of have a configuration in a way that the electrons can easily move between these energy levels.
Hello, everyone. Just a quick definition before we get into this next section of the episode. So this definition is to define 3,5 and 2,6 semiconductors. So what exactly are they? Well, 3,5 and 2,6 semiconductors are a way of broadly referring to and classifying two major categories of compound semiconductors. The designation 3,5 or 2,6 refers to which group in the periodic table the elements in the compound semiconductor are from. For example, a commonly studied 3,5 semiconductor material is gallium nitride, or sometimes called GaN for short because of the atomic symbols, where gallium is from the third group of the periodic table, and nitrogen, which in its ionic form is called nitride, is from the fifth group in the periodic table. Compound semiconductors contain two or more elements to form the semiconductor material, such as gallium nitride, whereas silicon only contains one element. We'll be talking a little bit more about the advantages and disadvantages of these materials in the next section of this episode. So we hope you enjoy.
So silicon is obviously the big name material in this space for the most part, but there are certain parts of this industry which are reaching some limits with conventional silicon-based semiconductors. So perhaps this is more in the space of 3,5 or 2,6 semiconductors would be in making this next generation of materials that will make a significant impact on the electronics field.
So let's talk about why silicon. Because again, It has dominated your electronic industry forever. And it's coming because A, it's very cheap and it can have a perfect crystal structure. You can dope it, make it as conducting as you want. You can make it as insulating as you want. It has a good combination of, charge carriers, which means the electrons and the holes and velocity. So you can do a lot with silicon. And it's coming to a limit. And that's why 3-5 semiconductors we talked about are coming up. Gallium nitride has been a very nice alternative, and especially for power electronics. Why? Because gallium nitride, A, it performs better as compared to silicon at higher voltages, at higher temperatures. It has much faster frequency speeds, switches faster. So all of these things that I talked about, which is, temperature, voltage, and frequency, what do they all drive into finally? Your systems to be more compact, faster, have lower switch losses, higher frequency, efficiency. All of these are better. So gallium nitride or 3-5 semiconductors for that matter is gaining interest. Obviously, they have some challenges like everything else. There are 3 that I can mention. The first one is 3-5 semiconductors are more difficult to handle than silicon. They're not as commonly available. And then they are also much smaller in size. They're like these massive 20-inch silicon wafers that you can work and make billions of transistors on. Here with gallium nitride, they're much more costlier and they're much smaller in size. Also, some of the other like gallium arsenide, just the cost of processing it, the facilities that I have, processing facility, they say will cost about 20 times more than on a silicon wafer, just to start with. So now you have to marry some of the properties of these new 3-5 semiconductors and some of the possibility of silicon together. And for that, there's a new material called as scandium aluminum nitride. And so it's combining both materials, your gallium nitride and your scandium aluminum nitride. And people, when they combine these two, they are lowering the energy demand that goes into making those. And they can work with larger pieces and use all the advantage that gallium nitride have, frequency switches and speeds and high voltage performance. All of these advancements are good and happening, but like I said, they are not the bottleneck for our next electronics. You may kill the research of making another of these fancy semiconductor devices because they're not bringing manifold advantages into it. Of course, the cost is a major problem. So other than the cost, performance-wise, we're not adding much value to it.
Okay.
So what drives, again, those advancements, those heterogeneous integration, that's where the new next generation changes in electronics would be.
So let's wrap up by talking more about some of that next generation electronics. I was wondering, Dr. Sharma, have you heard of Elon Musk's new company or newest company, Neuralink?
Mm-hmm.
So,
I have.
So for our listeners, Elon Musk wants to create a brain-computer chip interface that serves as a neuroprosthetic. It's basically a chip implanted into your brain that can send electrical signals from a computer, a very small chip, and you could do things like restoring movement to someone with a severed spinal cord. You could improve their hearing ability, regulate their hormone levels. There's a lot of potential there, even relieving your anxiety to an extent. So I wanted to get your expert opinion on this matter. He mentioned in a Joe Rogan podcast that this technology could arrive, within the next couple of years. Do you think that's feasible? It seems like it's very much in the early stages of development, but how far away do you think we are from this chip actually existing?
Yeah, it's coming from Elon Musk. So it has to be much more in future than right now. But let's look at what this is. You understand that we have this small chip, and this chip outside of a human body is nothing fancy. It's very ordinary. It does exactly what any other my $10 little chip will do. It's not any marvel in terms of material per se. It's a simple CMOS has already done what it's trying to do.
Yep.
Where is the key? Key here is how these chips will make the neural connection in the body. Right. That's where the problem is, challenges. They say they have brought these integration to nanoscale, and they're down to 1 millimeter cube volume. That's small, that is. It's like a nano dust, pretty much, like when it comes to the device itself. So there are challenges on how you're going to interface this with neurons reliably. That's the key. Whenever there's a human connection. It's one part of this system is biology or a bioproduct. The other one is an electronic device interface. Where's that interface? It's the neural connectivity and the viability. That's important. So there's going to be some impedance between these two. And then we want to lower this impedance as much as possible. Right? That's why performance will improve. And the other challenge is, how do you know where you're going to target? If you have to target it to the right nerve and the location, that's the challenge. First, you have this device, you have to make sure it is targeted at the right nerve and it makes the neural connection that is viable. Those two things cannot just happen by only MSE. There are people from VME, they're going to be people, they're clinical trials. It's a combination. It's this multitude of people who will actually do it. Let me tell you this. These devices, they don't have antennas. They need to talk to each other, right? Because we are working with such small dimensions that at those dimensions, antennas won't work. So what are the other kinds of fields that are required? We have ultrasounds. We've got purely magnetic fields. Human body without any metals, implants, anything of that sort in the body can take Teslas of magnetic field and go unperturbed. So those could be used. But again, those are some of the areas that people are focusing on. They have viability happening. But unless the interface with the nerves happens with the electrode systems that we're trying to make right now, it will be quite a bit into future before they can be seen into real people's body.
How far in the future do you think? Give me a number of years.
Are you going to come back and ask me what happened? So I think with all the different fields out there, maybe another 5 to 10 years would be a good time frame where these smaller miniaturized would be able to make it. But again, it is not just MSE. It has to come with a consolidated efforts from very different fields. Definitely viable. Not immediately, but within a decade. Yeah.
And so we've covered a lot in this conversation. We've really hit a number of subject areas here. So I'd like for you to bottom line it for us in terms of these different subjects that we've covered. So what are 3 things that our listeners should take away from this conversation of the role of material science in electronics packaging and electronics broadly speaking?
We'll start with the materials and their processes, not just materials themselves per se, processes also that goes in making them. They are the heart and the soul of any electronic, consumer electronic, bioelectronic, national security related electronics. Those are the heart and soul for it. The second most critical thing that I would like to emphasize here is it is not the material, dearth of material types or properties that are pulling us back in terms of advancement. It is the heterogeneous level of integration that's going on in today's electronics. All different kinds of materials, all different kinds of shapes and sizes and design structure. Unless we find a harmony, the interface, that drives the advancement in the future. And the third one, I would say, would be material science is probably still in its infancy. All it needs to do is talk to fields and areas of research into other parallel engineering fields. And I'm sure we can get into and improve the quality of the life of a lot of people. As a material scientist, we should drive ourselves not only in improving or making another consumer product better, but also in general, bring about the more conscious. I don't even know whether this will tie in that well with what I'm trying to say, but it's essentially because material scientists know what it takes to make that product, what it took from the earth, what it took from the resources that's out there already. We have to be more conscious. We have to rely a lot on ourselves than just more designs and more engineers that will improve the quality of life in general.
Thank you so much, Dr. Sharma, for coming on to our show today. We certainly learned so much about the electronics industry and how important material science is to make an impact in the future and how much it's affected our past as well. So we really appreciate you coming on to the show.
Thank you for having me. I enjoy talking to, the future engineers. Yeah. And that's what I think I like on my job, because I get to interact with you folks, the fresh minds and the fresh look at the things that people have been working for years or for such a long time. That fresh view comes from you. And it's always a pleasure to talk and share some of the findings and pick some of your brains.
So where can our listeners find you if they'd like to reach out to you?
So you can always send me an email. I am at Georgia Tech. I am first name Himani dot last name Sharma at GATSCH, georgiatech.edu. I am usually floating around in material science department on campus, but shoot me an email if you have any questions, or we can always virtually meet too, in case you would want to talk about anything. I'm more than happy to discuss with your audiences and yourself.
Thank you for tuning in to this episode of the It's a Material World podcast. We look forward to releasing our next episode in 2 weeks. But until then, if you want to hear from us, we are on LinkedIn, Twitter, YouTube, and Instagram. Search for us as It's a Material World podcast. Links to our social media sites will also be in the show notes. If you have any feedback, we'd love to hear it. We're just 2 college students looking to get started with a podcast, and we want to grow the show with our community's input. You can send us feedback through messaging on any of our social media sites. Feel free to also provide feedback by messaging us directly on LinkedIn, either to Punithu Upadhyaya or Thomas Miller. But until then, take care and stay healthy.